Hi. Today we're going to do some first principles, order of magnitude estimates in this problem. The point is that if you look at the Earth at any time, you see that most of the Earth, like more than two-thirds, is covered by clouds. But I mean, this is the kind of typical places where it rains. So we can say that most clouds don't rain. So how do you distinguish what cloud has the potential to rain? That's the question we are asking. And we're going to ask like how turbulence plays a role in that and whether there is a minimum Reynolds number or a minimum level of turbulence for the cloud to rain. Okay, so we're going to pin our thoughts, we'll take a cumulonimbus cloud, which is pretty tall, like it can be many kilometers tall, but for our calculations, we'll take it as 1 kilometer. And we're asking that we want rain of 1 millimeter to collect from this cloud. So if I keep a bucket, I want 1 millimeter to collect in it. And for this 1 millimeter of rain from this cloud, is there a minimum Reynolds number? That's the question we are asking. And to pin our thoughts, we are saying that the cloud base is like 1 kilometer above the earth. So this is obviously not to scale. It's millimeter and kilometer. Okay, so in a monsoon cloud or a very convective cloud, you have about 10 to the 9 droplets per meter cube. So this is a very high number density of droplets. And by condensation, like just because the surroundings in a cloud are super saturated, all the particles, all the droplets are going to become about 10 microns big. They're going to grow till 10 micron, and after that, the condensation is not going to help them grow big. So how are they growing further? And then we'll ask, like in a cloud of 1 kilometer with this many particles, how much is there like 1 millimeter of rain inside it when we start out? And it turns out there's like 4 millimeters of rain in such a cloud every kilometer. So there is more than enough liquid water for it to come down, but it may not always come down. So like now let's look at the cloud base. And from there, these droplets are now sedimenting, okay? And we have an evaporation time and a falling time, which are given by some constant times water density by the A. A is the radius of the droplet at all times in this top. So then you have a fall velocity which depends on the total height h above the ground and divided by the terminal velocity, which keeps changing when you evaporate. So now, in order for a droplet to even reach the ground, it has to reach faster than it evaporates, right? It has to fall faster than it evaporates. So chi should be greater than 1. And you see that there is a very minimum radius at the base, which is 70 micron. Any droplet which is below 70 micron is going to not hit the ground. So like in order for it to hit the ground with some reasonable radius, let's say that, it has to be an order of magnitude bigger than this. And we know that raindrops are about a millimeter. So we'll say that they're all millimeter sized droplets, order of magnitude, who are reaching this bucket. And so we need about 10 to the 6 1 millimeter droplets per unit area to get this 1 millimeter height here. So 10 to the 6 droplets, that's important. Okay, so now we're asking how did every droplet who became 1 millimeter, what was that droplet's history? So we know that as big droplets fall, we can do this calculation of a big droplet falling through smaller droplets. All the smaller droplets are 10 micron, that's a typical size, and this one falls faster. So based on the drag and based on the terminal velocity Vp of the big particle and Vp zeros of the smaller particles, we can write like how the big particle grows, like how many it collides with. That depends on the number density, that depends on the collision efficiency, like how many collisions result in bigger droplet growth. So now the thing is that this we can take to be about 10%, and n, we see that if n is too small, then there's going to be no rain whatsoever. This thing will never grow to 1 kilometer. And if the residence time inside the cloud is too small, that depends on how fast it falls and how big the cloud is, like the height and so on. That automatically gives minimum sizes of cloud and such things. But we are not after that. We're after turbulence. And then these are conditions under which there's no rain. if there's a convective updraft, it can help small drops live there for a little longer. So doing this calculation based on these things, we see that a 1 millimeter drop had to have started out at least a 100 micron drop at a kilometer height. So only then it's going to grow to 1 millimeter by the time it reaches here. So there are these lucky 100 micron drops. So somehow you have a small number of lucky drops who are already 100 micron who can become raindrops. And that is the thing that turbulence is going to create. So rain initiation needs a few lucky drops, small number, it's 10 to the 6 we calculated out of a total number of 10 to the 12. So this lucky drop is a 1 in a million drop. So 1 out of every million drops has to be lucky enough to start growing. So now in order to talk about whether you can have 1 in a million starting to grow, you have to go to the tiniest drops when everybody was 10 micron, and then you have to see whether it will grow or not. So now, all in turbulence, typically the small scale vortices, the very powerful vortices which we're after, are Lambosine in their cross section, their Gaussian cross section, and they arrange themselves in tubular structures. And when you have, so the point is that if you do a simple argument of whether a Kolmogorov vortex can form this, and we'll do that soon, you'll see that it cannot form raindrops. It cannot help in raindrop growth. So you need sub-Kolmogorov scales. And this is a very nice paper which treats, simulations with many tiny scale vortices, the intermittent vortices, and this based on the Kolmogorov scale, this thing is 500 times, square root 500 times more vortical. So these intermittent vortices are very needed. So in the simplest form, so what happens to droplets in these vortices? That's what we're asking. Here is a Lambosine vortex, and we're asking, the droplets are they just follow Maxi-Riley equation, where u is the velocity of the vortex, and you have this simple equation, and tau is the response time of the particle. In our case, it's about 2 milliseconds. So normally, these two movies play together. So this is a normal argument for turbulence, where you see that droplets from two different vortices can actually straddle the distance between them and come and collide, and due to collisions grow bigger. These arguments are not working for cloud, because for that you need a Stokes number, particle response time to turbulence time of order 1, and that never ever happens in a cloud. Like a Kolmogorov scale is half a second, and these are 2 milliseconds. So you'll never have Stokes of 1. So none of the standard turbulence arguments work for a cloud. So we are now going to look at the dynamics near these single very powerful vortices and see whether that can create enough seed. So now, like, you see that there is always a void created near these single powerful vortices, and this void volume goes as some circulation of the vortex times particle time scale to the half. So we can actually estimate the void area in 2 dimensions, and then we know the Lambosine vortex. We can estimate that the given this, we can estimate that you need a Stokes number of 1, greater than 1, for any particles to, any raindrops to collide and grow. So because we need, and this is a local Stokes number based on the vortex time scale. So like when the vortex becomes very rapid, similar to the particle time scale, you can have that. And the fraction of the void is proportional to the fraction of the lucky drops who join together to make big raindrops. Okay, so we can actually calculate that void volume very simply. So basically you have a vortex, and if you have a vortex radius bigger than the this special critical radius, you'll never have a void, and only the tiny vortices will form voids. You have to see how many of those tiny vortices are there whose powerfulness is greater than the time scale, 1 over the time scale square of the particles. And if you know that probability density, you can get the void volume, and you need a void volume of greater than 10 to the minus 6 for 1 in a million. So then, like, you can look at turbulence data, which I told you they do this very carefully. The void volume, the probability of the strength of the vortex is given by this stretched exponential, which actually collapses when you rescale it a certain way, which shows that extrapolation to cloud type Reynolds numbers is allowed. Like some of these big clouds have huge Reynolds numbers, which is allowed. So then we do this calculation, we use this probability to put it in the integral in the previous slide, and we can get a minimum Reynolds number for the void. So like we know that we need 10 to the minus 6, so that gives us this minimum Reynolds number. And we've extrapolated this to even bigger cloud Reynolds numbers. So the summary is that it says what it is there.
Thank you.